Hello and welcome. In this video I'll be covering section 2.2, which is over some rules for differentiation. My goal for you by the end of the video is to be able to find the derivatives of functions using the constant rule, the power rule, the constant multiple rule, and the sum and difference rules. So essentially this video is going to be a way to do derivatives a little bit more efficiently or quickly compared to doing the limit process that you learned in 2.1. So a lot of this video is going to be working through examples and just solidifying hopefully the rules that we cover as we go. So with this, feel free to press pause, skip forward, or rewind as much as you need to in order to be able to feel like you understand the concepts. So we'll go ahead and start with the constant rule. So the constant rule hopefully is going to be one that's relatively easy for you in that the constant function or a graph of a constant function is always just a horizontal line, and since a derivative is representing the slope, hopefully we can remember that every horizontal line has had a slope of 0. So mathematically what this means is we're going to, anytime we take a derivative of a constant, know that its value is going to come back as 0. The second thing we'll get into is the simple power rule. So essentially if you ever have something in this format, x to a power of n, at this point we would just take the power that we see right here, and what we do is essentially kick it out front, and then we decrease that power by 1. So this is again a shortcut for being able to do a very quick derivative without having to go through that whole limit process. So notice again the n that was the power moves in front as a coefficient, and then the exponent just decreases by 1. And what is important to note here with the simple power rule is n can just really be any type of real number. So even if it's not something that's a nice number, this simple power rule still works so long as the n is a real number. So it works with positives and it works with negatives. So let's work through a few examples here. So with this, I've intentionally kind of changed some of the notation and the names of the functions as well as the input variables, just to kind of show that this works in a number of different situations. So the instructions for each of these is just to differentiate each function, so find the derivative. This first one, f of x equaling -5, well, since -5 is a constant, I know that f prime, or the derivative of f, should then in this case equal 0. Letter B, very similar, y equals 0. 0 is technically a constant, so y prime in this case is also going to equal 0. And then the last one, g of t, so this time technically we'd be differentiating with respect to the variable t instead of x, but with this one it just has pi. Even though pi is not a perfect number, it still is considered a constant. So with this one, g prime of t once again would equal 0. So it doesn't matter if it's a negative, a positive, an irrational number like pi, the derivative of any constant, hopefully the moral of the story here hits home, it's always going to equal 0. So let's now go ahead and try and practice some of the simple power rule ones. So this first one, letter D, h of x equaling x cubed, essentially I'll take this power of 3, I'm going to move it out front and then decrease it by 1. So my derivative h prime of x is going to now have a coefficient of 3, and then the power on x decreases by 1, so it would turn into a power of 2. So my slope equation, or my derivative for that one, would just be 3x squared. Next one, f of x equaling x. Keep in mind there was always an imaginary power of 1 in that area if you don't see a power. So with this one, that power of 1 is going to move out front, and then the power will decrease by 1. So f prime of x in this case will equal 1 times, and then x now to a power of 0. But what we know about a power of 0, hopefully, is anything to a power of 0 has a value of 1. So for this particular one, I'd actually end up with f prime equaling just the value 1. And then the last one on this page, 1 over x squared. First thing I would want to do is rewrite that using exponents that are negative. So in this case, since it was on the bottom, I could move it to the top, make it a negative power. So now when I do the simple power rule, that power goes out front, so -2, and then it decreases by 1, so it becomes negative 3. And I never leave a negative exponent on my answer, so this would just turn into negative 2 over an x to a positive 3. So hopefully these 3 examples of each of those rules, the top 3 being the constant rule and the bottom 3 being the simple power rule, hopefully these have helped in making you understand how to approach these relatively basic derivatives. So let's go ahead and move on to 2 other rules, the constant multiple rule as well as the sum and difference rules. The constant multiple rule is essentially something that's going to allow us, if we had a coefficient in front of, say, some function, so notice in this case it would be this value c that's multiplying our function itself. Essentially what you can kind of do is just separate, or it's almost like you factor it out for a moment and then find the derivative of that function and then multiply those 2 results back together. And on the next slide I'll work through some examples that hopefully make that make sense. But again, if there's a coefficient in front of a function, I just get to keep that coefficient, and then when I take the derivative, if other parts turn into other coefficients, I would just multiply those 2 values that are in front together. The sum and difference rules is essentially what's going to allow us to, if we had like a long, say, polynomial, for example, where the terms are separated by addition or subtraction, what's nice about the sum and difference rules is I can just take the derivative of the individual parts. So like in this case, f of x plus g of x, that could be like a binomial where the f of x, say, is maybe like x squared, and then the g of x is maybe like 2x or something like that. I can essentially just take each individual derivative, f prime and g prime, and just keep the operation that was between them. So if it was addition, I keep addition. If it's subtraction, I keep subtraction. But the sum and difference rules really just allow us, for having something that's maybe like a higher degree polynomial, be able to just take derivatives of the individual terms and then add all of the results back up. So we'll go ahead and work through a few examples of this. Notice this first one, we have a function that has a coefficient, so I'd have this 5 that's multiplying the function x cubed. So I really just keep the 5 separate, and then just take the derivative of that x cubed, which from earlier, hopefully you remember the power would come out front, become a 3, and then drop the power by 1 on x. And so now I should be able to multiply those 2 coefficients together to get 15 x squared. So my f prime of x for this first example will just turn into a slope equation that would be 15 times x squared. Letter B here, probably want to rewrite this so I can see what that c value would be. So I have 2x to the 3 halves over 9. I could really call that 2/9 times this x to the 3 halves. So somewhat rewrite it so that I can see what the coefficient is. So again, that 2/9 is just going to stay put for a moment. I now would take the power that's on x, multiply it out front, so that would turn into 3 halves. And then the power on x will drop by 1, and if I subtract 1 from 3 halves, that would leave me 1/2. And now I should be able to, again, each of these were y prime. Actually, the first one was just y. Second one, if I use the correct notation, should be y prime to represent the derivative. And then this last one, if I go ahead and maybe try and reduce, looks like a 3 and a 9, I could reduce to a 1 and a 3. And then the 2's should be able to cancel down to a pair of 1's as well. So multiplying those 2 fractions, I ended up just getting that to turn into 1/3, and then x to the 1/2 still is just hanging out at the end. So I'll go ahead and do one more here with g of t. That's just utilizing this constant multiple rule. Again, rewriting this x to the 4th in a slightly different way. So I haven't taken a derivative yet, so I'll use the g of t notation. This is just going to be 4/5, and then times, and x to the 4th in the denominator really is the same as saying x to the -4. So now if I actually apply my derivative here, or my simple power rule to that part, I've got my coefficient 4/5 that stays. That power will come out front, so it turns into a -4, and then drop by 1 for the exponent, so it would become -5. And at this point, if I go ahead and try and simplify, looks to me like I'll end up getting 16 fifths, but negative, because there's one negative sign, so negative 16 fifths. And that x is a negative exponent, so I could drop it to the denominator to make it positive, so I'd end up with a negative 16 over 5 times x to the fifth. And that would be my simplified version of that specific derivative. So now let's go ahead and practice a few of these sum and difference ones that maybe combine a little bit of the constant multiple at the same time. So notice this letter D example, or h of x equaling x squared plus 8x plus 12, that quadratic. To find the slope equation for that, or the derivative, I'll essentially just take each individual derivative and then just add or subtract them together. In this case, they're all going to be addition. So x squared should turn into the 2 moving out front, and then x now having a power of 1, so just 2x, plus the next one, the power of 1 that's on that x will come out, multiply with the 8, so that's just going to turn into 8, and then I'd have x to the 0, which is just equal to 1, so 8 times 1, and then the derivative of 12, that's a constant, so we can fall back to our constant rule and know that that's going to turn into 0. So my real h prime of x equation, or derivative here, is going to be 2x plus 8. Moving on to letter E, looks like with this one I might need to do some simplifying because I do have an x in a denominator, so I'll need to utilize a negative exponent. I also have a power on a parenthesis, so I will need to apply that both to the number 2, but also to the power of x, or to the base of x, rather. So with this one I know cubing 2 would give me 8, so I've got a coefficient of 3/8 on this one. And then cubing x is just x cubed, but since it's in a denominator, I'd want to move it to the top. So I'm just rewriting it. I'm not doing any derivative yet. I'm just dealing with where that x was, because the power rule required it to be in the numerator. And then the next one, I'll just keep it as is, because that one looks like it's already in a position where I can utilize the rules that we've been talking about. So let's go ahead and take the derivative then of this first one. So I'd end up with negative 3 that's going to multiply with that 3/8. So that would really turn into a negative 9/8. And then the power should drop by 1. So negative 3, if I subtract 1, should turn into negative 4. The next one, the 3 is going to multiply with the 2 in front. So I'd end up with 2 times 3 being 6. And then the power drops by 1 to x squared. So it looks like I'm pretty close other than that negative exponent, so I'll go ahead and just do my last simplifying step and drop that to the denominator of that fraction. So basically just down with that 8 and make it a positive exponent, and then I still have the negative 6x squared that's afterwards. If you wanted to take the time to get a common denominator and combine them together to make it a single fraction, you could do that. Wouldn't take too long, but I'm not going to require you to do that. It's ultimately something where if you needed to plug into a derivative function, I'd let you make the decision whether this is easier, or if you combine them to make it a single fraction, whether that would make it easier. Anyway, on to the last example on this slide. Notice with this one we've got some radicals. So remember, radicals, if we rewrite, it's always whatever the power inside is goes in the numerator, and then whatever the index is of the root will go in the denominator. So this 5th root of x squared really is the same as saying it's x to the 2/5 power. And then a square root, remember there's an implied 2 right here, so this will just turn into 2 times x to the 1/2 power. So now if I go ahead and apply the power rules and the constant multiples as well, I'd have 2/5 would come out and multiply with 3, so that would turn into 6/5. And then it would drop by 1, so think of subtracting 5/5. So that would actually have to turn into negative 3/5. Then I've got the second one here is going to have 1/2 times a 2. Well, that's just going to turn into 1. And so I don't need to really write that as a coefficient, but now my power drops by 1, and so 1/2 take away 2/2, or 1 whole, would turn into a negative 1/2. So each of those ended up with some negative exponents, so I'll just move them to their corresponding spots. First one, 6 is the only thing that will be in the numerator. 5 times x to the positive 3/5 would be on the denominator. And then the next one, the coefficient 1 will stay on top, and then I'd have x to the positive 1/2 in the denominator. If you wanted to switch those back to roots, more power to you, but again, you do not have to do that. So again, everything in this video is pretty much going to be example driven, so pretty much everything from here on out is just going to be some more examples. So it looks like to me I've got 3 more slides to go of just different ways that these problems can be presented. So again, feel free to utilize this however you would like. Press pause and rewind, or look for these types of questions in your homework and watch it, then press pause, work through those problems, and then come back and revisit the video, however you want to use it. But these ones now, as you can see, it's going to be a little bit more application style. Instead of just a plain old find the derivative, now it's going to have some follow-up questions. So this first one asking specifically to find the slope of this function at a specific point 1, 3 that lies on the graph itself. So it's basically, another way this could be presented would be to like find the slope of the tangent line at that specific point 1, 3. So subtle change in wording of the question, but it would be the exact same approach. So again, this keyword slope basically means I need to find its derivative, because the derivative equation represents the slope, and then I should be able to plug into it. So the first thing I need to figure out is what is f prime of x. Since this is just a polynomial, 3 terms, I should be able to just take each individual derivative and then add or subtract them together. So the first one, x cubed, is going to turn into 3 times x squared. Move the power out front, then drop it by 1. Next term, 2 times x, that's just going to turn into a negative 2, because the power of 1 would multiply with 2 to stay 2, and then drop down to a power of 0, so that x to a power of 0 will just turn into a 1, and then technically add the plus 4, but since that's a constant, I'd end up with a plus 0. So after a while, you can get to a point where every time you see a constant, instead of writing the plus 0 at the end, you can go ahead and just know that there isn't another term at the end of that you would need to do. So now it's actually finding the slope at that specific point. So that would be doing f prime at, since x is the only variable I need to plug in, it's really just going to be this 1 that I need to figure out. So I just plug that in, so that would turn into 3 times 1 squared. Then take away 2. Well, 3 times 1 would be 3. Take away 2, that would equal 1. So the slope at 1, 3, on this function at least, is going to be equal to a value of 1. If we move on to the next one, where now actually wants the equation of the tangent line. Remember, to find the equation of any line, I need to know a slope and a point. That did give me a point that it wants to pass through, so really all I need is a slope, and then I'll have to use the point slope form to come up with the actual equation. So in this case, it gives us our function. I'm going to go ahead and just figure out what the derivative is so I can get the slope at that point. So again, this first one, I have a negative 1/4 multiplying with x to the 4th. So simple power rule, that 4 would come out and multiply with a negative 1/4 to turn into a negative 1. And then times x, and that power would drop by 1, so it'd be to the 3rd. The next one, the power of 2 is going to come out and multiply with the 2 in front to turn into a 4. And then the power drops by 1, so it would turn into a power of 1. And really, anytime you have a power of 1, you could technically just leave it as a single x. And then the last one, minus 1, that would be a derivative that equals 0, so I'm not going to worry about writing plus 0 at the end. So now we need to figure out what our slope is at that point. So I need to do f prime of, since the only input is x, I only need the x value of that point to come up with a slope. So that would be essentially doing negative 2 cubed plus 4 times 2. Well, negative 2 cubed, that would really be negative 8. And 4 times 2, that would be 8. And if I add those together, I get 0. So that's kind of nice that my equation here has a slope of 0. So if I use point slope form, it would be y take away y1 equaling my slope times x take away x1. But 0 times that whole parenthesis is just going to turn into 0 on this side. So really I just need to add 3, and I get that y is equivalent to 3. So this would be a horizontal line for our tangent at that specific point. So we'll move on to a couple more examples, and this one, the intent of these is to show you at least some strategies to try when things look like they're a little bit tougher or they don't fit maybe the rules as perfect as the previous examples maybe have. So with the first one here, as you can see, we have a product of two parentheses. So right now it's already still not fitting the profile of any of the rules we've covered so far. So what we would want to do is just multiply out those parentheses and get it to where it maybe does look like something that we've already done. So I end up having here f of x just equaling, and if I expand this out, I'd get 2x cubed. Then I've got an x squared times a 1, so that would just be x squared. Then I've got a 3x and a 2x to get me 6x squared, and a 3x with a 1 to get me 3x. So it looks like there's a couple of terms that can combine, so I'll go ahead and do that before I start doing my derivative process. 2x cubed as my first term, middle two can add together to give me 7x squared, and then still the plus 3x at the end. So now I've got this into a format that I can just take the derivative of each individual part. There's no parentheses in my way. So I'll go ahead and just do my simple power rule as well as the constant multiple rules. And the 3 will come out and multiply with that 2 to turn into a 6 and drop the power by 1, so x squared. The middle term will turn into 2 times 7, so 14, and then drop the power by 1, so that would just turn into a power of 1, so I can just leave it as a single x. And then the last one, 1 times 3, would just turn into 3, and then the x would have a power of 0 on it, which has a value of 1, so I really don't need to do 3 times 1. So my derivative for this first one, notice once I got the parentheses out of my way, just by multiplying it out, it turned into something that I could then just take 3 individual derivatives to come up with the overall f prime. With g of x over here, and I guess example B, what we can do is anytime you have fractions like this, you can split it up into 3 separate, or in this case, since there's 3 terms on top, that's why I'd be able to split this into 3 separate terms where just every single one of them gets that denominator of x squared. My hope is that when I do this, that each term potentially might be able to reduce with what I have on the bottom, or that I could maybe just rewrite it using negative exponents. So this first one, notice I end up having a couple of terms that can reduce. X to the 4th divided by x squared can just turn into an x squared, so that coefficient 3 is just going to stay. The next one I have that coefficient of negative 2, but x cubed divided by x squared would leave just a single x, or x to the 1st power. And then the last one, there weren't any x's for that one on the bottom to combine with, so this one I do just need to rewrite it using a negative exponent. But now I've turned it into something that fits those rules that we've talked about thus far. So I should be able to just find a derivative now of each individual term. First one, 2 times 3 will give me 6. Drop the power by 1, so power of 1 on that x. The middle term, 1 times a negative 2 would just be a negative 2. Drop the power by 1, so it's a power of 0, so I don't have an x on that one. And then the last one, I have a negative 2 times a 4, which would be a negative 8. And then drop the power by 1, so negative 3. So I do have one extra step with this one that I needed to do, or need to do, which is just rewrite it so I don't have any negative exponents. So this last one I would just need to drop that x cubed to the denominator so it would become a positive power. If you wanted to get a common denominator and turn that all into a single fraction, you by all means can do that. It's just not necessarily something that you have to do. Alright, so on to our last examples. Notice with this one now it's a little bit more intense of a question. It's now asking us for a specific point or points at which the function has a horizontal tangent line. So if the tangent line was horizontal, what we would know is the slope of any horizontal line is going to equal 0. So essentially what these problems are going to have us doing is instead of saying that m equals 0, since it's giving us a function, we're actually going to say when is f prime of that equal to 0. In other words, when does the derivative equal 0? Since after all, a derivative represents the slope. So the first thing I'll need to do here is figure out what is f prime of x. So with this one, 2 would come out front, and then the power would drop by 1. Next one, 1 would come out, multiply with the 6, so it stays 6, and then the power would turn into 0, so there's no more x, and then the constant always turns into 0, so that is my derivative. So now what I'll do is just set 2x minus 6, that derivative equation, equal to 0, and start trying to solve it. So the first thing I would do is move the 6 over. That would then give me 2x being equivalent to, I would have to add 6, positive 6, and then divide the 2 over to get that x is going to equal 3. So I know now the x-coordinate of my point. I just now need to figure out my y-coordinate. Well, the y-coordinate should just come from the actual function itself. After all, that is the actual collection of all the points anyway. So I'll just need to figure out what is the function at 3 so I can get its corresponding y value. So that would just be 3 squared, take away 6 times 3, and then add 5 to that result. So that would turn into 9, take away 18, which is negative 9, plus 5. So that should really turn into a negative 4. So the point at which this has a horizontal tangent would be the point 3 comma negative 4. So again, important to take note of with this one, I needed to do the extra step of getting a y, and a y will always come from the original. After all, this f prime represents slope, so anytime you plug into a derivative, you're going to get a slope answer. Anytime you plug into the original function, you're just going to get a y value. Let's go ahead and do the last one here. Same start, need to figure out what is my derivative. So with this one, the 3 would come out, and then power would drop by 1, and then I'd end up having the next one is just going to turn into a negative 12 because the power on x would turn into a power of 0, so it drops the x term. So I'll just set 3x squared minus 12 equal to 0. Looks like I could factor a 3 out, and that would leave x squared minus a 4. But then I could go ahead and just divide that 3 over to give me now x squared minus 4 just equals 0. X squared minus 4 is a difference of 2 squares, so I could factor that to get x plus 2, x minus 2. So now if I set each parenthesis equal to 0, I'd end up getting negative 2 from the first parenthesis and positive 2. So it looks like this one had 2 points at which it had a horizontal tangent line. So I'll have to plug in 2 different values to get their corresponding y. So f of negative 2, if I plug that in, that's going to be negative 2 cubed, then minus 12 times negative 2. So that would turn into a negative 8, and then it looks like plus 24. So that would turn into a 16. So one of my points, if I go ahead and just maybe put it here at the bottom, that I'll circle later, is going to be negative 2 comma 16. Then I do the same thing here now with positive 2, so this would turn into positive 2 cubed minus 12 times positive 2. So this turns into positive 8, then take away 24. So this one looks like it would turn into negative 16. So my other point happens to be at 2 comma negative 16. And so there's my 2 points where a horizontal tangent line would happen. And where we're going to start heading towards with this is if you think about a horizontal tangent line to a graph, those actually would have to be like a maximum value or a minimum value or a place where my graph has turned. So each one of these, you can kind of probably make the assumption that negative 2 comma 16 is probably a relative max, whereas the 2 comma negative 16 is probably a relative min for this graph because that's the only place where horizontal tangent lines would happen. So this is just a different way of kind of identifying some extra key points with graphs that eventually we're going to start taking advantage of that. So anyway, hopefully this video has been helpful and has more than enough examples for you to be able to feel confident working through the homework. But as always, if you have questions, just let me know and I'll do everything I can to make it make sense. I appreciate you taking the time watching the video, and until next time.